Good afternoon, everyone. Welcome to the 8th session of online faculty development program on smart civil engineering practices to contemporary issues, organized by the Department of Civil Engineering, NSS College of Engineering. So today we have the speaker, Dr. Balu E. George. So I would like to invite Dr. Nisha A.S. to welcome Dr. Balu E. George to this session.
Yeah. Thank you, Kirti. Good afternoon, dear participants. Today we have Dr. Balu E. George, the resource person for the current session. He took his BTech degree in civil engineering and MTech with a first rank from MG University. He received his PhD in civil engineering from IIT Madras. For his doctoral dissertation, he worked on helical piles. He is currently working as Assistant Professor, Department of Civil Engineering, MAC, Kodamangalam. He also has coordinated student projects funded by SERD and KSCSP. He has to his credit notable publications in high index journals. Apart from IST, he also serves as a life member of other professional bodies like Deep Foundations Institute and Indian Geotechnical Society. On behalf of Department of Civil Engineering, NSS College of Engineering, Palakkad, I would like to welcome the speaker for today's session, Dr. Balu E. George. Over to you, Dr. Balu.
Thank you, ma'am. Thank you, coordinators. I hope I'm audible.
Yes, you are.
Yeah, thank you. Now, first of all, thank you so much for such a generous introduction. I really believe, I wish my wife was around to hear all those nice phrases that you've showered on me. And so these are the presentation that I'm about to take now includes two things. Broadly, it's something related to geotechnical engineering, some smart solutions, smart to me at least. Now, before we start with the presentations, I have two anticipatory bails to put forth. One is that I'm not used to the Google Meet kind of thing because this is the first time I'm presenting something on an online platform, and I'm taking my baby steps in that. So if there's any technical glitches that may creep in during the presentation, please excuse me. Now, second is that since I've tried to squeeze in two different topics into the presentation, I'm not sure if I'll be able to finish that with, let's say, 3 or 3:15. So if it spills over 3:30, just feel free to stop me in. And that's about the introduction. Now, going to the topic, these are the contents. I have a smart pile design to propose, the idea, the methodology, the results, and that is a part one of my presentation. Now, the part two is about stability of finite slopes. It includes stone column support embankments, a brief study on that, and that is a part two. Before we go into the detailed technical things, I've always found that the FDP workshops, at least the ones that I've presented or the ones that I've been a part of, this will be the expectation, right? You'll have to sit through for, let's say, 1.5 hours. But what really happens would be like this, right? After maybe 45 minutes, we all lose our concentration. So this is a difference which I've seen during the usual FDPs, the expectations and the realities. Much worse case here, right? If it's an afternoon session, you can expect this. I hope I'm not as boring as I used to be earlier. And but what really happens in the online platform could be this, right? When you have the Google Meet with the video, you'll be like this. And when you have the Google Meet with the audio, you can switch over the mic and the video, and you can go to your sleep. So I'll try to understand that. It's bound to happen even to me, so I can try to understand that. Let's see what happens now. When the organizers, Nisha ma'am and others, proposed the name of the FDP to the smart civil engineering practices to meet the contemporary issues, I was thinking what smart is, right? What do you really mean by a smart solution? Now, the word smart has crept into our dictionary usually off late by this, right? You have a smartphone in our hand. We're all having a smartphone, perhaps. I mean, at least 60% of you would be seeing this video through a smartphone. Now, why is that a smartphone? To me, the Nokia phone that we used to have earlier, at least 15 years back or 10 years back, was not as smart as the one that we have now, right? Because largely due to the fact that you can't play around with different applications in the Nokia phone, whereas in the smartphone that we have, even if it's shipped once we have bought that, you do have different options to play around with different apps, right? You can include different new apps, you can update your programs, etc. You can play around with these things. Whereas in the previous mobile phones that we used to carry earlier, the applications and the solutions they offer were quite limited, right? Likewise, if I compare some geotechnical practices with a Nokia and a smartphone that we have different smart solutions. One prominent smart solution could be the use of numerical analysis tools, right? Now, researchers and academics who are in the meeting would agree and would resonate with my opinion that numerical analysis has gone way beyond the practical uses. I mean, you can once you validate a solution, you can play around with different parametric variations and get a solution from the numerical analysis. So that is a smart solution, at least to me. And one such smart pile design is the first presentation. Piles in clay, you very well know that they take load by two different methods. Number one is an end bearing, where the load that comes over the axial load is entirely taken by the bearing at the tip, right? So that's an end bearing pile. Now, even if that end bearing pile is installed in clay, the load is taken by the rock up to which you have installed the pile, right? So that's entirely taken by the end bearing. Whereas you have another thing called the skin friction, or the friction piles in clay, where you don't expect the rock to be present beneath that, right? You would be forced to install the pile in a sand soil profile where you can't expect the presence of rock. So you are actually forced to design the pile in such a way that the entire vertical load is taken by the skin friction, right? So that is a thing that we call as a friction pile. Now, obviously, there's no completely friction pile and completely end bearing pile. These are all theoretical things, as you would probably agree with me. Now, in end bearing piles, you know that QU is equal to QP. QU being the ultimate load, to QP, which is the tip resistance. Whereas in skin friction, QU is equal to QS, which means the entire vertical load that you apply onto the pile is taken by the skin friction. Now, when you go into some theory portions, these are the basic things that we're all familiar with. The static method is a theoretical method that used to estimate the load carrying capacity, right? Where the ultimate failure load, QU, is a sum of QP and QS, right? Let's say you have a pile of length L, it's acted upon by QU. That QU is shared by QS and QP, right? QU is equal to QP plus QS, but QP is the end bearing resistance and QS is the skin friction. QP, the point of the tip resistance, and the QS, shaft resistance, or the skin friction. Now, QP is again equal to small qp multiplied by AP, where small qp is the bearing resistance per unit area, and AP is the cross-sectional area of the pile. Now, QS is equal to Fs into AS, where Fs is a unit skin friction, which could probably due to the sand or maybe due to the clay's adhesion. And AS is the circumferential area of the pile, depending on the geometry, of course. If it's a circular pile, you have pi dl. If it's a square pile, you have the perimeter multiplied by the length, etc. QP, the bearing capacity. AP, the area of the pile tip. Fs is a skin friction or adhesion along the shaft. And AS is the effective circumferential area. Now, when we come to the term Fs, you can have two options, right? If it's sand, you have K into sigma V into tan delta, where K is the earth pressure coefficient in the lateral direction, sigma V is the vertical stress, and tan delta, delta being the angle of interface friction, right? The angle that's mobilized, the internal angle is mobilized at the surface of the pile and the soil. When it comes to clay, you have Fs equal to alpha into C, where C is the effective cohesion, the underlying cohesion, and alpha is the adhesion factor, right? So adhesion factor alpha, you have C cohesion, you have delta as the angle of internal friction, interface friction, I beg your pardon. Sigma V is the effective stress, K is the lateral earth pressure coefficient. Now, the presence of clay is quite crucial in these two cities. These two cities are the hubs of development. We know Kochi is one example, Chennai is another example. These cities are hubs of development, but at the same time, most of the clay deposit, most of the sand, the soil deposit that they have there is clay, right? So in usual cases, you'll be forced to design the pile in such a way that the entire load is taken by skin friction, right? Like this. You can't expect a rock to be present even if you dig up to, let's say, 20, 25 meters. And you don't have the luxury of pumping in money to go beyond that depth at some cases, right? You can't go infinite depth to see if there's rock present. So these conditions, you'll be forced to make the pile stand in such a way that the entire load is taken by the skin friction. Now, when we talk about that, I'll give you two examples, right? The normal pile that you have here is called a prismatic pile, which means the cross-section area remains the same. You have a circular cross-section, it remains the same throughout, unless it's an under-rim pile. Now, I can take two examples here. Number one, I have a pile here. Number two, I have a pile of the same length, but with a bigger diameter, right? Now, the first pile, you know that the tip area is less compared to the right side. So you can expect less tip resistance. And you have less surface area. So you can expect less skin friction. And you have less volume. So the investment that you have on the material cost is also less. Whereas when you have the same pile with the same length, but with a bigger cross-sectional area, which means you have a bigger diameter, you can have everything more, right? You can have more end-bearing area, so you can have more resistance there. You can have more surface area, so you can have more surface friction there. But you'll have to compromise there, right? Because the material input is also more. Now, this is where we have the role of under-rim piles. Now, these are nothing but the piles in which the base area is increased by providing a bulb, right? What we call as a bulb here. Now, this is a single under-rim pile that you see to the left side, where you have usually a diameter of 1.25 times the shaft diameter. So that's a bulb diameter there. And to the right side, you can see a multi-under-rim pile, or double under-rim pile, as I used to call that. And there you have two bulbs kept at a specific spacing, right? So the principle is quite simple. You increase the end bearing. You increase the base area, so you increase the end bearing. And when it comes to the theory portion, I've taken a pile with a B shaft diameter and a B1 bulb diameter, and I have cohesion at the pile tip as C, and cohesion at the bulb level as C1, and cohesion at the shaft level as C2, right? And let's say AS is the circumferential area of the shaft. In such a case, you have point or the tip resistance as QP into AP. And for clay, you used to take QP as CNC. You don't take the three different terms of Terzaghi's equation. You limit everything to CNC, where NC is taken as 9, usually for deep foundations. NC is the Terzaghi's capacity factor is taken as 9. And for under-rim piles, AP turns out to be AB, which means the area of the bulb. Now, for shaft resistance, QS is equal to FS into AS, and FS turns out to be alpha into CS, or alpha adhesion factor, multiplied by the cohesion. And when it comes to an under-rim pile, you have three different terms here compared to the prismatic normal pile. The first term, 9C into pi by 4 B square, means that it is a tip resistance at the shaft. The second term, 9C1 into pi by 4 into B1 square minus B square, is a bearing taken by the bulb level, right? And the third term, alpha C into AS, is a skin friction taken by the shaft. So for a single underring pile that you see in the slide, you have the option to estimate the ultimate capacity using this equation. Whereas when you have a multi-underring pile, like the one that you see to your right side, where you have more than one bulb, uh, the logic is deceptively simple, I'd say, because you have two things here. Number one is a point resistance, the same that you have seen earlier, 9c into pi by 4 into b square, plus the end bearing at the bulb. And the shaft friction is a bit complicated here. The shaft friction is not distributed entirely along the length. It's instead distributed along the shaft, right? Because you have a bulb here and a bulb below that, so you can't write that equation there. So alpha c into as is the shaft resistance, but the space between these two bulbs, you have different phenomenon there, because when you try to squeeze this pile down, what really happens is that the soil between these two bulbs will tend to move along with the pile, right? Which means it acts as a part of a pile. So here you have what we call as a circumscribing cylinder of soil, which means you have the soil in a cylindrical form, which circumscribes these two bulbs, right? So when you consider that into account to calculate the ultimate bearing capacity, I have a different term called CA into ASB, which means the entire pile's capacity can be calculated by not three terms, but four terms. First term is the usual term that we have seen earlier for a single underring pipe. Second is again the same thing, the bearing at the bulb level. Third, alpha c into AS is the shaft friction at the shaft. Whereas the fourth term, you don't have alpha, instead you have C into ASB, where ASB is a circumferential area of the cylinder. Now, just believe that the cylinder is not concrete, the cylinder is soil. So you don't have an interface friction here. What you have instead is a soil-to-soil friction, right? Just imagine you are trying to squeeze this pipe into the ground, you're applying a load. So this soil will act as a unit of the pipe. So the friction that's mobilized is along the soil-to-soil interaction and not at the pile-to-soil interaction. Now, that is a key point that we're interested in. And ASB is a surface area of the imaginary cylinder. Of course, it's imaginary, and it's circumscribing the bulbs. And CA dash is the average cohesion at that level. So to put the long story short, you have QU is equal to first term, which is the shaft tip resistance. Second term, you have the bulb tip resistance. Third term, you have the shaft friction resistance. And the fourth term is a cylindrical soil-to-soil resistance, right? So this happens in a double underring pipe. You don't have the fourth term in a single underring pipe. Now, this is a key point that we are interested in. Now, literature survey, as this, by the way, was part of an IICT-funded project, which was carried out a few years back. So a few literature surveys were carried out to understand the mechanism of underring pile with two bulbs or more. And we found out that the best literature that we have is this, right? Indian Standard 2911 Part 3, IS code for pile. And you can see the dimensions they have marked here, suggesting at what depth the bulb should be placed and the angle at which the bulb should be cut, etc. Now, to the right side, you can see a double underring pile, right? We'll focus on that. In the double underring pile, you have the code says that the diameter is D and the bulb diameter is DU. And if the bulb diameter is DU, the spacing between these two bulbs is always good to have in the range of 1.25 to 1.5 DU, which means if you have the bulb diameter to be 1 meter, the distance between these two bulbs would probably be around, let's say, 1.2 meter, right? Now, that's the literature survey part. Now, based on that, we came up with a design which we think is smart, and that's, of course, there's a scope for criticism, by the way. The prismatic pile is shown to the left side. You have a bigger prismatic pile, right, of a bigger diameter or a bigger radius. The third option is to have a single underring pile. And the fourth option is to have a double underring pile. And the proposed pile would look like this, right? This is our target pile, which means you have more than 2 bulbs, but the bulb diameters is not as big as the conventional ones that we have, right? In the conventional one, the bulb diameter, let's say, for an example, if you have a shaft diameter of 30 centimeter, the bulb diameter would be around 70, 80 centimeters. Whereas in the proposed pile, when you have a shaft diameter of 30 centimeter, you don't have a big bulb. Instead, you have a small bulb of 50 centimeter, just an example. But the number of the bulbs is not limited to 2. Instead, you have it almost distributed along the length of the shaft, right? So this is a pile that we are proposing. I mean, studies are almost through that. And when you talk about the capacity, when you try to understand the capacity, this is what really happens. When you have a single under-ream pile, we know the equation. When you have a double under-ream pile, we know the equation with an extra term which has a circumscribing cylindrical soil. So when it comes to our pile, you have the same cylindrical soil, right? Which runs from the first bulb at the bottom to the top bulb at the top, right? So instead of this volume, you have the entire volume of soil to soil interaction, which means alpha term, or the adhesion factor, which is always less than 1, by the way, is only mobilized in this portion where you have the interaction between the soil and the pile. Below that, you don't have the interaction between the pile material and the clay. Instead, you have the interaction between the clay and the clay, right? Just imagine you are trying to squeeze, I mean, you're trying to jack this thing down. So the interface is not concrete to clay, instead it's from clay to clay. So alpha can be assumed to be 1, right? Whereas in the area above that, alpha turns out to be less than 1. Now, again, the figure here, I've taken B as the shaft diameter of a smaller pile, B1 as the shaft diameter of bigger pile, and we have here the new pile with the shaft diameter B, the same B, with the bulb diameter B1, right? Which means you don't invest the same volume of concrete as you see in this prismatic pile, but the only increase in volume is when you have the bulb, right? These areas are the only increase in material input. And again, an anticipatory bail to be put forth is that this is not applicable in sand, right? When there's a clay which has a cohesion of, let's say, around 30 kPa to 40 or 50 kPa, and if it's stiff, this pile is applicable, because you need to make sure that once you cut the bulb inside the hole, it should stand on its own, right? It should not collapse. So this pile, under-ream pile, by the way, is applicable only to clay soil, right? I used to have this comparison to an alwa, right? This pile is anyway, any under-ream pile can be made practical and feasible when you have the clay consistency in such a way that it resembles the normal alwa that we use, right? Otherwise, what really happens is out in the field, the cavity tends to cave in, right? So you can't expect the same kind of geometry. You can claim that you have constructed the under-ream pile, but what really happens is that the cavity may have caved in, and you don't really have that geometry inside there unless you have this kind of a clay, right, where you can cut the proper bulb. The example that I've taken is a B of 30 centimeter, which means the slender pile of 30 centimeter, and B1 is 50 centimeter, right? So the proposed pile will have a shaft diameter of 30 centimeter with a bulb diameter of 50 centimeter, in contradiction to the 80 centimeter range that we have in practice. The methodology, like I said, you have 2 things. One is the experimental investigation, and second is a numerical investigation. Experimental investigation, we had taken a site in Cochin because Kochi is quite famous for the Cochin marine clay, right? And basic standard tests were done in site. This figure, by the way, is we conducting a standard static compenetration test, CPT test, to estimate the soil properties, right? And CPT test was carried out. Vein shear test was carried out to estimate the cohesive strength of the clay beneath that. And the field vein shear test is shown to the right side. Based on these two examples, I mean, based on these two tests, you can estimate the range of cohesive strength, right? And in field. And SPT, standard penetration test, was dynamic CPT, DCPT was also done. And of course, DCPT is not really a necessity, but we just kept it as an option in case some other test failed to provide us good results. So these four tests were carried out to estimate the soil properties, right? Standard penetration test, dynamic concentration test, static concentration test, and vein shear test. Now, we casted the piles. For us to compare, we had 5 or 6 piles casted. The first two piles are nothing but the conventional piles, right? The prismatic one, no big complication, just simple piles. Now, when it comes to casting of underream piles, this is the usual underreaming tool that we use inside, right? This is just a photograph that I had taken. Now, the diameter is marked here. 30 centimeter is the diameter, which means you'll get a pile of 30 centimeter diameter casted. Now, 80 centimeter is the diameter of the bulb. Now, this dimension is as per the Indian standard codes, right? IS 2911 Part 3 specifies this dimension, the usual underream dimension. So once you employ this underreaming tool at site, what you get is this one, right? You have a 30 centimeter shaft and you have an 80 centimeter bulb. That's a single underream pile. The same thing goes here as well. You have a double underream pile, same geometry, 30 here, shaft diameter, 80 here, the bulb diameter, and the spacing is 100 centimeter, which means you dig a hole down to the bottom, you employ this underreaming tool, you cut the bulb here, the bottom bulb, you raise the tool upward, you cut the next bulb there, and you lift the soil up. So once the casting is done, you can expect the pile to be of this geometry. Now, that's a usual underreaming tool that is in practice in the industry. But when it comes to our underreaming tool, this is a proposed pile design, right? So we need to develop something which is suitable for this pile design. You don't have to go for 80 centimeter diameter. Instead, you have to limit it to 50 centimeter. Plus, your number of bulbs is not limited to 1 or 2. Instead, it's limited. I mean, it can go all the way up to 5 or 6, depending on the length of the pile. So 30 and 50 here, and based on that, we devised a new underreaming tool. The prototype is just shown here, right? It's not a field model; it's just a prototype. So when at rest, it looks like this, just like an umbrella mechanism. When you jack a rod at the top, it kind of turns to this shape, right? So I can cut 2 bulbs here, the spacing of which can be designed, the diameter of which can be designed. So what I can fundamentally do is that I can lower this. By the way, this is just a prototype design. I can lower this into the soil. I can apply a force on the top. So these wing kind of mechanism goes into the soil, and if I rotate it, I'll get a bulb, right? So you lower it and jack it down, rotate it. So what you get is something like this, a new pile design. And we fixed the diameter to 30 centimeter shaft and 50 centimeter to bulb at a spacing of 62.5 centimeter. Now, the field procedure, of course, it includes any other practical applications of a pile casting. You take a borehole, you lower the reinforcement cage. This is nothing but the details of reinforcement cage, and then you cast the pile. So you can see in the field there's a line of piles being casted here. One was of a prismatic pile of 30 centimeter. Another one was 50 centimeter. Then you have a single underream pile. Then you have a double underream pile. And though it doesn't fall into the picture, you can there's another pile, which is a new pile method that we have proposed. So you have 5 piles in number aligned in a single line, right? Onto which we are trying to have a pile load test done. So the piles were casted at site, and these are the specifications, the volume of concrete consumed. Take a look at this. Now, the normal pile of 30 centimeter diameter had consumed 0.318 m³ of concrete. Whereas when you have 0.5 or 50 centimeter diameter, the volume escalates almost up to 2.5 times here, 0.883 m³. But the new pile is just around the same volume, right? You have 0.3 here, which consumes 0.318 m³, whereas the new pile just consumes around 0.375 m³, right? Which means the material input, the volume of the material input, is quite comparable to the 30 centimeter pile, and that will turn out to be an advantage. Now, like I said, everything that you talk in the design office might not get implemented in the practical application, right? So to ensure that our proposed pile has gone up to the design depth, we carried out a sonic pile integrity test. It's a load strain test that we do to ensure that the pile has gone deeper to the depth that we have proposed. PIT test was carried out, and the pile load test was done. This is just a photograph of the site where you can see the pile load testing being carried out. And now, as per the code specification, Indian Standard Code specification, you have safe load criteria listed like this. Part 9 of the same 2911, when part 4 of the same 2911, says that the safe load can be the least of the following, right? 1, it's a 2/3 of the final load at which the total displacement is 12 millimeter. 2, 50% of the final load at which the total displacement is 10% of the pile diameter. Is when you have 30 centimeter diameter pile, you have 3 centimeter displacement. So whatever load that corresponds to 3 centimeter, you take the half. So these are the pile code specifications about the safe load criteria. Now, based on the pile load test, you'll get a few graphs like this. These are just the sample graph that I've chosen to put into the slides. The load settlement curve, you have load versus settlement, load in kilonewton, settlement in millimeter. This example, the one that you see into the slide is for a 30 centimeter diameter pile. And you have another example of a 50 centimeter diameter pile. Then you have the multi-tiny bulb, or the one that we have proposed, the new pile, that'll have something that'll have a load settlement curve like this. Now, don't bother looking into these load settlement curves. We'll compare that. Now, for the sake of comparison, this is a load taken for 12 mm settlement. P 0.3 means that you have the conventional pile, 30 centimeter diameter, 4.5 meter length. Now, that carried a load of 93 kilonewton, or whereas a 50 centimeter diameter pile, same length, 4.5 meter into the ground, carried around 150 kilonewton, or 15 tons. Whereas the new pile that we have proposed, which has a shaft diameter of 0.3 and a bulb diameter of 0.5, carried almost around 142 kilonewtons, comparable to the 50 centimeter diameter pile. So just think of this. You have the load which is comparable to the 50 centimeter diameter pile, but you have the material input comparable to the 30 centimeter diameter pile. Of course, this happens only in clay, and which is listed here, right? The percentage increase in load carrying capacity is listed here, and the percentage increase in volume is listed here. So compared to 30 centimeter diameter pile, 50 centimeter diameter pile shows 57% increase in load carrying capacity, but that comes with a compromise of 177% increase in volume. Whereas the new pile gives the 58%, almost 58%. I mean, these results are sample results, I should admit. There were a few other tests carried out, so it averages out to 58% at a material increase input of just 18%. which means you can have an economical result from the new pile design. Now, yeah, this is almost the same table. These are the geometries of pile tested, right? I have A, B, C, D, and E there. A is 30 centimeter conventional pile. B is 50 centimeter conventional pile. C is a single underring pile. D is a double underring pile. And E is a new proposed pile. So the percentage increase in load carrying capacity is listed here, and the percentage increase in volume of material is also listed here. So I've highlighted these two things, 177 and 18.87%, the one that we've discussed in the previous slide, which means when you have B, which is a conventional pile, 50 centimeter diameter, you have 57% increase in load carrying capacity at 177% increase in volume. Whereas when you take a look at the pile type E, you get 58% load carrying capacity at just an increase of 18.87% of material input. Now, people who are working in the field would probably resonate with my opinion that let's say 1 m cube of concrete would cost you around, let's say, somewhere between 10,000 to 12,000 rupees if it's not reinforced. So reinforced concrete can go all the way up to 17,000 rupees per meter cube, including the contractor's profit. So when you have this difference in material input, it's a huge difference in economy, right? So that's a key point that we'd like to stress. Now, part 2 is the methodology in the numerical investigation. Now, just to rewind, we have done the field test. We have taken the soil parameters based on static CPT, the dynamic CPT, the SPT, and the lab tests were carried out, etc., etc. And we have the actual data of the load test in hand as well. Like I said in the introduction, that is not really smart, right? Because when you think of the actual expense of the experiment that you have done in the field, it was around 1.5 lakh, maybe more than that, maybe north of, let's say, 1.8 lakhs, including the pilot test. So it's not really smart because you can't play around with different geometries there. So you have a smart solution of numerical investigation, right? Now, why not conventional analysis? Part 1 is that conventional analysis is expensive. Like I said, the test took a toll of around 1.8 lakhs on our pockets. So we don't have to play around with much geometries there. Other few reasons why we don't go for conventional analysis is that in conventional analysis, we're all civil engineers, we do have assumptions, right? We assume that the soil is homogeneous. We assume that the soil is isotropic. We assume that the soil is elastic. We assume that the soil is semi-infinite. Now, these are the assumptions, the usual culprits, right, which creeps into any theory, the assumptions. But we can mock at it. It's not really that way, right? Soil is never homogeneous. Soil is never usually isotropic. It can't be usually elastic. And semi-infinite, you can agree to that to a certain extent. But usually these assumptions are flops, to put it bluntly. But for the sake of analysis, we need to have the assumptions. In short, assumptions are nothing but the demerits, right? The demerits are the reflections of the assumptions. So why numerical analysis? To understand the mechanism of load transfer, because at field, you can't see what really happens inside the soil, right? You don't have the option to dig the soil and just try to see what really happens when the load is being transferred. So for us to understand the mechanism, the numeric analysis is good. Now, second thing is that you can expand, you can augment the spectrum of investigation, right? Like I said, we just limited our studies to 5 different piles in field due to economic constraints. But you do have the luxury of augmenting the spectrum, trying to play around with different parameters. So that flexibility is involved in numerical analysis. So that's different. I mean, that's definitely a smart solution in line with your FDP's title. So the software was Plaxis 2D. Of course, 3D was also carried out. We'll go into that later. And the pile, every pile that we have considered as geometry is axisymmetric problem, right? You can cut in half and model the first half, and whatever result that you get is representative of the pile. So that's an axisymmetric problem. You take 15 order triangular elements, and the pile is assumed to be linear elastic to concrete. you have soil assumed to be more Coulomb model. Of course, you do have different models available, but to admit that more Coulomb is the best and the easiest model. There are better models, but to estimate the soil parameters and to input that soil parameters, MC model, more Coulomb is the best. Now, how do you get the input parameters? You have the undisturbed soil sample that you get from the SPT test, plus you have the UDS sampling tubes inserted into the soil. So based on that, you take the UDS undisturbed sample to the lab, you extrude that, right? So once these are extruded, you can carry out whichever test that you prefer. It can be triaxial test to determine the shear parameters. You can have the Casagrander's experimental procedure to get the liquid limit, the plastic limit, etc. And so based on this flowchart, the UDS sample taken to the lab, extruded, then carried out to the triaxial test chamber, and then you get the input parameters. The input parameters are, number one, E, Young's modulus of soil. Number two, number two is C, cohesion of the soil. Then you have internal friction phi. Then you have unit width gamma. Then you have dilatancy angle, right? So you can somehow estimate almost every parameters based on the undisturbed soil sample that you have carried out to the lab. Now the boundary condition, like I said, this is axis symmetric problem. You have half of the pile cut to the right side, which means the soil volume is double the one that you see on the screen. And 4.5 meter was a pile length. The boundary that we have chosen was such that the failure falls within the boundary. So 3.5 meter to the right side, 6.5 in some experiments, and we have gone up to 10 meters in some others. So nonetheless, this is a representative soil model that we have used in Flaxus 2D. 3.5 by 6.5 meters was the geometry. Rigid boundary, which means you don't allow salt to get settled beyond the bottom boundary, but it's allowed to settle, right? Which means the left and the right boundaries act as roller supports. People who are working with finite element analysis would probably be knowing these things. This is nothing but the standard fixities, right? The bottom is fixed, but the sides are rollers, right? So the same thing, standard fixity gets applied here. And the global coarseness parameters was such that fine mesh, you do have different options, coarse mesh, very coarse mesh, medium, and then fine, very fine, etc. So finer the mesh, more accurate can the expected results be, but the finer the mesh, it takes a lot of time for the computer to run the program and get you back the results. So after a few trial and error methods, we found that the fine mesh, which falls in between very fine and medium, was quite normal. It gave satisfactory results and was suitable. Now, with one exception, that the areas where the stresses are large, you can have the option of mesh refinement. But I'm not sure if this gets applied to the latest version of Flaxus. It used to be the case earlier. You did have an option to refine the meshes there. So the mesh refinements were done, and these are the steps. You have this is geometry, by the way, 4.5 meter, 30 centimeter first one, 50 centimeter second diameter, 30 with the 80 bulb there, double under rim pile there, and the new pile design there, right? So these analyses were run, and these are the steps. You have initial phase, the calculation of initial stresses. Second phase is the installation of pile, and the third phase is the simulation of loading, which is by a prescribed displacement, which means you apply a displacement onto the pile, which is equivalent to the displacement suggested by the IS 2911. Now, this one gives you a flavor of how the deformation pattern would look like, right? You have the double underring pile there. You can see that the soil tend to move along this line, right? Between these two bulbs, the soil has a tendency to act as its own unit, right? Which means when you try to jag upward, the soil between these two bulbs will try to act as the same unit as a pile, right? So this is given by the stress contours, the deformation contours. So left side, you can see the double underring pile in axis symmetric condition, and the right side, you can see the single underring pile. Right, now when it comes to conventional pile, The prismatic one, the deformation contour looks like this. To the left side, you can see, and to the right side is our new pile design, right? You can see that from the first bulb at the bottom to the topmost bulb at the top, the stress contours, the deformation contours, tend to circumscribe the bulbs, right? Which is the same thing that gets reflected in the theory, right? The circumscribing soil cylinder. Now, this is the one that mobilizes alpha is equal to 1, which means along this line of soil connecting these two bulbs, you don't have interface friction between concrete and the soil. Instead, what you have is soil to soil adhesion, right? So that behavior gets reflected in the Traxxas analysis as well. Now, just a representative load deformation criteria from the Traxxas 2D, and this is a comparison of the load capacity. The same notation A, B, C, D, E I've written there, conventional to underream to double underream to the new proposed pile. Comparison from the Traxxas shows that the same thing. When you have E, which is a new pile design that we propose, it gives around 58%, right? Yeah, 58% increase. Whereas for B, it gives around 57% increase in load carrying capacity. Almost in sync with the load test results that we got from the field. Now, comparison with the load test, you can see that ABC is listed here, A, B, C, D, E is listed here, but I've just limited it to A, B, and E because that's the one that we are interested in. We are no longer interested in underream piles any longer. So A, B, and E shows that the percentage increase turns out to be around 61% for 50 centimeter diameter pile, whereas it's around 57% for the new pile, for the Traxxas based analysis. Whereas for the, you can see the comparison listed there. 61 is here, 57 is here, and you can have 52 there and 58 there, right? So, which means that the analysis results of Traxxas is almost representative within the tolerance level with the pile load tested field. Now, again, once we have the model validated, you can play around with different combinations. I've tried to play around with the spacing there, just a sample representation of the image I've put here. I've tried to play around with the 1 DU spacing, 1.25 DU spacing given by the code, 1.5, and it goes all the way up to 2.5 DU spacing, where the spacing between the bulbs is 2.5 times the bulb diameter. So even in that case, you can see that the load taken for 12 millimeter settlement is at the peak when you have the bulb diameter, the bulb spacing around 1.25 to 1.5 times the bulb diameter, right? So this is the cusp of the graph, which means the maximum load is taken here at 1.25 to 1.5 spacing, right? So lower the spacing, you can't expect much higher capacity. Even higher the spacing, was done at a cohesion of 20 kilopascal. So the long story in short, we can say that the IS 291 specification of 1.25 to 1.5 diameter spacing seems to be quite logical, right? It's just, again, to augment the spectrum of analysis, we try to extend that to Traxxas 3D as well. So the same story, so soil is more coulomb, almost the same things that we have done, except for the fact that in 2D is axisymmetry in geometry, right? And the same thing, boundary conditions, it's fixed in at the bottom and allowed to move in the roller direction. And the input parameters were the same. Same steps, calculation of initial stresses, installation of pile, and simulation of loading over the top. So this is the soil volume that you have in 3D. I have different layers here because at site, you had a top 1.5 meter with the filled soil, and below that you had clay of different cohesion. So I've tried to represent them in different colors for us to understand that there are different layers there. So this is a soil volume 7 meter by 7 meter in plan, and 7.5 to 8 meters in depth, right? In which you have 4.5 meter pile. So that was a model. Now Cashier software is used to model that, and the model was imported to 3D Plaxis and looks like this, right? And this is a double underrim pile, by the way. It's not the pile design that we have proposed. Nonetheless, the procedure remains the same. So Cashier gets imported to Plaxis 3D, and yeah, I'll try to run a video now. I'm not sure if it works. This video shows how the pile deforms under loading, right? You have the underrim pile there, double underrim pile. You apply the load, and this deformation pattern seems to be like this, right? Again, you can see that the deformation pattern is not going into the soil between the bulbs. Instead, it tries to form a circumscribing cylinder there. I'll repeat that video. Right, you have the pile installed, you load the pile, and right. Usually I tend to insert these videos thinking that those who are sleeping, usually in any classes, tend to get attentive during a video presentation. I was just trying my luck on that, but when you have, yeah, when you have that kept on a figure, it looks like this, right? The same underrim pile, the stress contours, the deformation contours, I beg your pardon, is shown here. I've cut this section there and tried to show how it looks like. Again, this is not quite informative, but we're all happy seeing good colored pictures, right? And this, by the way, gives us an idea of how the mechanism really works, right? The soil between, you can see to the right side as well, the soil between the pile bulbs tend to act as a single unit. So that gets reflected in the analysis as well. Yeah, this is a new proposed pile design meshed here. I've taken a zoomed picture, and when it goes into the soil volume, it looks like this, right? You can see the deformed pattern, and you can see the meshed pile alone to the left side. The stress contour of a prismatic, the conventional pipe would look like this, right? You can see these lines goes all the way up to the top without much of a difference, up to 4.5 meter ground level. This is a prismatic pile there, which doesn't have a bulb, whereas for our new pile of the same shaft diameter, but with a few bulbs peppered into the shaft, it gives a deformation contour like this, right? Quite the same thing that you have seen in the video, if you have seen that, by the way. Quite the same thing. The stress contours tries to circumscribe these bulbs and goes all the way up to the top. Comparison, the final comparison is like this, right? The material input is quite low in our case, whereas you get a higher capacity. So based on the pile load test, you get a 93 kilonewton here. In Plaxis, it gives you 66. In 3D, it gives you 89. 150 here, 109 here, 120. And the percentage increase in load capacity is also given there. So I'd like your attention to the last column. Last column says that the percentage increase in load carrying capacity is 40% in case of a conventional pile, which, by the way, has 177% increase in volume, whereas in a new pile, it almost gets up to 40% at an extra percentage of just 18%, right? So what you fundamentally get is a higher capacity pile with a lower cost. Now that's a long summary in short, and these are the conclusions. The increase in load carrying capacity of the pile is 52% compared to the pile of 0.5 meter diameter, and 61% compared to 0.3 meter uniform shaft diameter. Whereas the new pile consumes just 18.8% concrete, extra concrete, and the 0.5 meter conventional pile will have an extra volume of 177%. So this is the advantage that we see here. And again, for the sake of comparison, we can see that the value obtained from the Plaxis analysis and the pile load test is almost showing the same trend. Plus, the last conclusion can be that the Indian standard 2911 specification of keeping the spacing between 1.25 to 1.5 seems to be logical, right? You were able to mobilize the frictional capacity when you have kept it, the spacing to be 1.25. Now, again, like I said, from the conclusion, the phenomenon is quite simple. At a lesser increase in concrete, you get a higher capacity due to the fact that alpha, the adhesion factor, is 1, right? So that's a key point, which I feel is a takeaway. Now, like I said, the limitation, of course, when you talk some theory, you should talk about the limitation. The limitation is just that, I mean, at least the one that I know is that it's applicable just to clay, right? Like I said in the first few slides, it should be ALVA, right? It should be self-standing. So if it's an ALVA constituency, consistency, I beg your pardon, it can have this underrim pile cut in the proper geometry. Whereas it's definitely not applicable. Anyone who think it would be applicable would be foolish enough to think that way, because sand never stands on its own, right? Even if it's confined to a depth of, let's say, 4.5 meter, you can't expect sand to stand on its own when you have the cavity of 80 centimeters, right? So your criteria is to have self-standing soil, a clayey soil, to cut the bulb, and not the mixture, right? We need alva and not the mixture, because in alva you can have self-standing, but in a mixture you don't have self-standing. You can expect the cavity to collapse. Now, yeah, it's almost free. Again, I'm not sure if I've bitten more than I can chew, but still, if your condition is not like this, I'll just try to, not sure, so I'll just try to continue with the presentation, by the way. The part
Yes,
2.
please.
Yeah, thank you. Yeah, the part 2 is the stability of a finite slope, right? I should admit that this is not related to the first part that we've discussed. The first part is about a pile capacity. The second part is about the stability of finite slope. Again, this is something which I thought was a smart solution. And excuse me. Now, embankment failures is where we try to focus on slope stability. You can see to the left side, there's a picture of an embankment which got failed due to deep-seated failure, right? Which means it's something related to slope and stability. Of course, the embankments are constructed on slope. Embankments are artificially made slopes. So it's constructed on slopes, and whatever slope stability analysis we can propose, it gets applied to embankments as well. Now, to the right side, you can see a notorious road, by the way. It's Adimali Munnar Road, right? I work at Kottamangalam, which is the foothills of the Munnar. So we used to travel in this road, Adimali Munnar Road. So whenever there's rain, at least in one stretch of the road, you can expect something like this, right? It's a slope failure. The major causes of slope failure, I'm sure you agree with me, the human factors. Number one, not properly compacted soil. It doesn't apply here, by the way. It does gets applied where you have an embankment. And second could be the monsoon, right? The right side picture that you see to the right side is definitely due to monsoon, because when you have water, it increases the unit weight, adds weight to the soil, so it can't stand on its own, it fails, right? Simple. So you have human factor, you have monsoon, and you have inadequate soil bearing capacity, right? So the embankments which are on paddy fields, you might have probably traveled in such cases, right? You might have a road. I'll give you an example later. I think I have. Yeah, this one. This one, people who are from Alapi side would know that this is the AC road, the Alapi Chengnasheri road, the AC road. Now this is a typical road. This was constructed. You can see that there's a road traveling. I mean, road stretching between Alapi and Sangnasheri. At the same time, to the right side, depending on the direction of your travel, by the way, you can see a canal, right? So the canal was dug out, creating the canal, and a few volumes of the soil was used for construction of the Alapi Sangnasheri road. So you have the embankment here, and to the right side you have the canal, right? You have the embankment, and then you have the canal. So you can expect something like, yeah, by the way, this is a picture which I had taken from the Manorama. This road is famous, notorious for this inundation of water in the rainy season, right? And yeah, you can expect this failure there, right? Let's try to see that this is AC road. To the right side, you have the canal there, right? In canal, you don't expect strong soil to be present, so you can expect deep-seated failure. It looks like this, right? So embankments try to fail that way in usual cases. Now, when it comes to embankments, like I said, it's nothing but a slope, right? You can define the theories associated with slopes. You can try to associate that with the embankments as well. So slopes tend to fail at this direction usually. It can be defined rotational failure. Rotational can be like this. It can be like this, or it can be like this, right? It can be toe failure. It can be slope failure, or it can be base failure. Right. Now, or it can be translational failure as well. Translational failure means that you don't have the failure surface represented by a part of a circle, and for the same reason, you can't apply radius there. Instead, you have a parallel plane there, right? It tries to fail along a plane parallel to the original ground. So that's a translational failure. And you have a compound failure there, right? It's a combination, as the word suggests, of the rotational, initially a rotation, and then a translational. And then you have the wedge failure, which means looks excuse me, let me take a sip of water. The failure would be like a wedge, right? So that's a wedge failure. This figure, by the way, it would probably give you a taste of how our first experience with slope stability is, right? We have all done this at least once. Maybe if you are not related to this Chinese students, maybe you can relate to this figure, right? We have all done this. So this is your first experience probably with slope stability. So every intuitive things that you can extract from this figure gets applied to the theory as well. Why I say is that this is a quote which I've almost get attracted to. I mean, if you can't explain it simply, you don't understand it well enough, proposed by Einstein. So since we know our experience with this one, we can define the theories. Now, theory is basically the balancing act, I'd say. Balancing act of the resisting force and the driving force, right? So slope instabilities are balancing acts. Resisting force prevents failure, and driving force promotes failure, right? And like we said, the usual resisting force is the sheer strength of this clay, of the soil, and the driving force which promotes the failure is usually the gravity and the water, right? So the balancing act gets upsetted when you have the slope instability, right? When the force which promotes the failure, which drives the failure, gets above the one that prevents the failure, you can definitely expect slope instability. So that's a fundamental thing, right? Now, water, it has two actions on the slope instability. One is water adds to the weight, right? When you have a unit weight soil of let's say 18 kPa, when water gets added to that, depending on the volts ratio, it can have a unit weight all the way up to 21 kPa, right? I mean, not kPa, kilonewton per meter cube, right? So 18 gets increased to 21. So it definitely increases the weight of a volume of soil. Number two is that it erodes the base, right? When you have a slope constructed, water, number one, it adds the weight, it adds the self weight, which promotes the failure. Number two is that it has a tendency, when you have a flowing water, it has a tendency to erode the base of the slope. I have a picture. Yeah, this picture This picture is, this is one desperate attempt from my side to promote myself. We did nothing here, but still we took a picture there. This is in Bhudathankettu. What really happened here, I believe, was that water tried to erode. I'm not sure if you can see there's an embankment to the top left corner. Water tried to erode the soil at the base, right? Plus it add water. This was 2 years back during the infamous flood that we had. So the Bhudathankettu Dam, this site is quite near to that. So the water tried to erode the soil, so it decreases the base resistance and the slope got unstable. Now, some boring theory, I'll skip that. Now, for us to analyze, you have 5-0 analysis, right, for slope stability. People who teach geotechnical engineering would agree that 5-0 analysis is limited to clay soil, right? The 5-0 analysis, you have Swedish circle analysis, where you cut the different slices into and then analyze one slice, then you put together some rudimentary form of finite element analysis, I'd say, because you fundamentally cut one, analyze one, try to stitch into everything together. So that's a Swedish circle method. Third one, you can have friction circle method, right? A bit more different one. You assume there's a friction circle there and the normals to be tangential to that circle, etc., etc. So there's a friction circle method. Then you have the most easiest one, the Taylor stability number. Taylor has done everything for us. We just have to look into the charts, get the stability number, and get the factor of safety. Now, these are just the theory portions. If you are interested, you can go to the, again, just a self marketing strategy, just a desperate marketing strategy from my side, YouTube, and try to search my name, that you'll get the details of these analysis. Even I didn't want to do this, but still the students these days, after the COVID-19 pandemic, we had to do this, right? You had to upload the videos. So I have a few videos of these analysis details uploaded there. Now the stabilizing methods, when you have a slope about to fail, you can have different options of stabilizing, right? You can terrace, right? You divide the slope into terraces. Number two is a water diversion method. Like I said, water can have a driving force there. You can prevent it to creep into the soil, so you can have a diversion method there. And then you have geogrid reinforced walls there. Geogrids can stabilize the walls in a slope. Geogrids, by the way, is, I believe it's constructed in AC roads as well. They have collaborated with the Coir board, and I think it's there. It's not the artificial one, it's the natural geogrid. And then you have graniting, right? Shotcreting. Then you have gabion walls. Again, it's a slope retaining method. Then you have soil made walls. And then you have stone columns. I've kept the stone column to the last because that's the one thing that I'd like to discuss if I have the time. Stone columns is another option to stabilize the slope. Now, stone columns are nothing but semi-rigid piles, I'd call them, because you are fundamentally following the same principle of installing a pile, either a displacement method or a replacement method. But instead of concrete, what you do is you fill in it with aggregates, the broken stones, right? Partly due to the reason that it enables us to extract water out. If there's consolidation, stone columns act quite like PVDs, right? It allows water to escape out, so you can have rapid consolidation. Plus, it can actually act as a load-carrying structure, quite like pile foundation, right? So it comes somewhere in between these two roles. It's also called as a granular pile, and is for flexible structures and for liquefaction mitigation. It can be constructed by vibro replacement or vibro displacement or by ramming. Now, these are the few landmark applications of stone columns. People who have been to the Gulf countries would identify with this picture, the 7-star hotel there. But it's not the 7-star hotel that they've constructed in stone column. Instead, it's this, the Palm Jumeirah, right? A part of that Palm Jumeirah, the island, which looks like a palm island in the plan, was constructed using the stone column. If I were to go with the information provided by the internet, this was constructed using stone columns, right? So you can have advantage of consolidation plus the advantage of load carrying capacity. The plan arrangements, again, can have square plan arrangement or a triangular plan arrangement. I'm sure you're familiar with these things. Square plan arrangement is shown to the left side, and triangular plan arrangement is on the right side. And of course, based on that arrangement, you have different unit cell diameters and areas and replacement areas, the smear zones, etc., etc. Right? So nothing but the influence zones. So square patterns and triangle patterns, plus, the failure mechanism, it can fail by buckling or by settling, right? Uh, buckling or bulging, what really happens is that to the left side, you can see that when you apply load onto the stone column, it tries to bulge out, right? Quite similar to the triaxial test, right? You have a soil cylinder there, and you apply the deviated stress, it tries to bulge out. So that's one type of failure. Or else if it can act as a rigid kind of a body and settle down, right? So these are two failure mechanisms. Now, encased stone column is a presentation that I'm prepared for. It just means that instead of just inserting the broken stones into the ground, you really encase them in geosynthetics, right? Like this, right? The picture that you see to the bottom, it shows homogeneous soil, which means you don't have anything there. To the right side, the second one is a composite. And then you have the semi-rigid, which is the encased stone column. Then you have the rigid, which is the pile. So encased stone column has a behavior which falls in between the composite stone column, ordinary one, and the pile, right? So it's semi-rigid in behavior, which means the chances of it getting bulged out can be minimal, right? So it confines the stones, it enhances the passive pressure, and you can have longer stone columns, you can have a higher degree of compaction, etc. Right? Increased bearing capacity. These are the advantages which can be proposed when an encasement is given. Now, I've written ESC, encased stone column, or EGC, encased granular column. You'll see these notations in the progress of the slides. And another advantage is that it prevents clogging, right? When you have the usual ordinary stone columns installed, chances are high that it gets clogged, which means obviously you are inserting it into clay. So once it gets clogged, the property of drainage gets affected there, right? So when you have encasement, you can ensure that the drainage for which it is designed is mobilized at the field, right? Encasement prevents the clogging, it aids the drainage, and it aids the load carrying capacity. Now, yeah, I'll just rush through these slides. Construction of EGC is like piles two things, displacement or replacement method. I'll just rush through these slides. Displacement just means that you're displacing the soil, pushing the soil sideways, inserting the stone column in the broken stones. Whereas in replacement, you dig out a cavity, just like the board cast in situ pile, you dig out a cavity, lower the encasement cage with the broken stones into it, and you keep it there, right? Of course, the first method, the displacement method, results in stress generation, whereas the replacement method, it has minimal stress generated. Like I said, this is a research work carried out, I should admit, not entirely due to my contribution, but I was partly involved in it. So with the permission of my friend, I've taken a few slides from that. And this research was carried out, my friend, while I was doing my research at IIT. I was involved partly in this. So now, when you come to stone column research, a lot of research was done on the axial load capacity, right? A few researchers were involving one single stone column, a few others involved a group of stone columns, etc. But rarely was the research carried out subjected to shear loading, right? Every research that we had then was subjected to axial loading. We didn't have the shear loading, so that is a gap, right? The research gap. People who have done the research would agree that we find a lot of time invested in finding a research gap, right? So once you get the research gap there, the shear loading, you're trying to understand that. Now, why are we interested in shear loading on a granular pipe. You can see a picture there, right? So let's assume the same thing. You have AC road, Alappuzha Changanaശ്ശേരി road constructed on an embankment, right? Beneath that you have clay, right? Of course, it's spanning between Kuttanad and Changanaശ്ശേരി, so you can expect nothing but clay there. So when you install stone columns, these stone columns at the middle of the embankment are largely subjected to vertical loading, right? Whereas as a slip circle passes like this, a portion of the stone columns, usually to the toe of the embankment, is subjected to lateral loading, right? So usually the ones that are at the center of the embankment is under axial load, whereas to the right side, the toe, you predominantly expect it to take shear loading. I'll give you a better picture. Yeah, some are under axial load, some are under shear. Yeah, this picture would give you a better understanding. To put things in perspective, the one circle that we have marked in red color gives you a case where the the slip surface passes through the stone column and it has induced a shear loading, right? Quite similar to the direct shear test. So I've zoomed in that, we have zoomed in that, and this picture shows that these columns to the toe direction are not predominantly under axial loading, instead it's under shear loading, right? So of course, we need to have an understanding on the shear capacity of the stone columns. Again, methodology, I'll try to rush through this. Part A is experimental investigation, and it was done in a large direct sheet box, not the one that we all have probably in our colleges. The one that at least I have, is of a 6 by 6 centimeter incline. So the large direct shear box is of a higher dimension, right, of 30 by 30 centimeters, and you can have a better understanding of the mechanism there. So a large direct shear box was carried out. I mean, the test was carried out in a large direct shear box, and with the stone columns, with encasement and without encasement, and a few different cases of encasement. Now, this is a sequence of experimental procedure. Number one, place a steel tube inside the direct shear box, right? Then you fill sand around that. Second picture says that. Third picture, you place and compact the aggregate into the tube. Excuse me. Then you take the tube back, remove the tube, and what you get is a granular column. So this one simulates the replacement method, right? You're not jacking the stone columns into it. Instead, you are kind of replacing the soil and filling it with stone. So that's a replacement method. This was the aim of the study, to quantify the improvement in lateral resistance due to OGC, which is ordinary granular column, and EGC, encased granular column. Tests were carried out under different confining pressures and normal stresses. 15 to 75 kPa stresses were given. Now, OGC means ordinary granular column, and EGC means encased granular column. Right, these are the combinations of tests. Number one is you have a granular column at the center. Number two is a granular column set in triangular pattern, 50 millimeter diameter and 100 spacing. Number three is a square pattern of the same diameter, 15 millimeter diameter granular column, but at a different pattern, square pattern. So you have single one, you have triangular one, you have square pattern, right? Test on GC and without geosynthetic encasement was carried out, and I'll not take the trouble of detailing everything, but the test summary is here, right? The poorly graded fine sand was used with 36 angle degree. Granular column 50 millimeter and 10 millimeter in diameter was used, and aggregates were used as stone columns, and three different geosynthetic materials were used as well. Number one is a woven geotextile, which we have marked as E1. Number two is a socks, cotton socks, E2. Number three is a paper towel, E3. Now, this is a test summary. Sand alone was tested. 50 millimeter diameter stone column was tested. 100 millimeter diameter stone column was tested. Again, 50 millimeter in triangular pattern was tested. 50 millimeter in square pattern was tested. And replacing the sand dense aggregate provided, which means the entire box was filled with dense aggregate. So these are iterations that was carried out. Of course, I've kept an acknowledgement to my friend Sunil from his journal. I've taken these details, by the way. These are some of the observations. Now, failure mode. When you talk about the failure mode, two broad failure modes were seen. Number one is a type 1 failure mode to the left side, where the entire thing got sheared off at the predefined failure plane, right? You're familiar with the direct shear box where you have a predefined failure plane. So the box at the bottom moves to one side, and the geosynthetic encasement failed as such. It got torn off, right? So that's one type of failure, failure 1. And number 2, type of failure number 2 is to the right side, where it didn't get broken entirely, but it kind of bent out, right? It got tilted. So that's failure number 2. Type 1 failure, where it got totally sheared off along the shear direction, was observed when the geosynthetic material with a high initial modulus but a low tensile strength. Obviously, that's quite intuitive, because when you have a low tensile strength, chances are high that the encasement gets teared off, right? So that those materials, E3 material with a lower tensile strength, got sheared off, whereas type 2 was observed for any material with a higher tensile strength, right? Higher tensile strength materials, encasements, they kind of offer resistance against shearing, so you can expect that to fail this way, right? Kind of bend out. The advantage here in type 2 failure is that, like we said, drainage is one function of a stone column, right? So if there's a case where the stone column gets totally sheared off, you can't have a continuous drainage path. Whereas when you limit the failure to the second failure mode, you can ensure that even if the load is not entirely taken by the stone column, you can at least ensure that the drainage is proper, right? So we actually prefer failure mode 2 in field, because even if it fails, it at least gives us an advantage by giving a drainage path. Part B methodology is numerical analysis. Again, I've not included the details because we are running short of time here. The model was created in FLAC, fast Lagrangian analysis of continuum. FLAC 3D software was used, and SS Mock-Column was used. And geosynthetic encasement was a geogrid type shell element, and the computer detail is given as well, right? You had a workstation there to process the volume of data that you put in. The model validation was done, a sample result of which is shown here, right? You can see the experimental and the numerical direct shear box results compared here. So in almost every 15 to 75 kPa confining pressures, after trial and error methods, you can see the agreement there, right? Experimental and numerical method results tend to agree, at least most of the time. Now, right, these are some of the observations. Again, I'm limiting observations to a few slides here. 50C OGC means that 50 is a diameter, 50 millimeter diameter stone column. C means it's at the center of the direct shear box. OGC means it's not encased, it's ordinary. So 50C OGC's stress pattern is shown here. And it can be seen that higher stresses is generated behind the granular column in the upper part of the direct shear box. Let's try to imagine what really happens. You have a direct shear box here. You move the direct shear box there. The bottom box moves, and it tends to have a higher shear stress induced at the portion which is behind the granular column, right? So this is a case where you don't have an encasement. Passive force generated is due to the movement of the granular column. When it tends to move, the rear portion of the granular column tends to push against that, so you have passive force mobilized, so that gets generated as stress. Whereas when you have the same geometry, but with encasement, EGC, what really happens is that you limit every stress is generated within the column, right? The stresses are minimal there inside the box. Highest stresses are generated inside the granular column compared to the surrounding soil. So you're not stressing the surrounding soil. In our case, you're not stressing the alapy clay. Instead, you are taking the trouble into the geosynthetic encasement, and every stress is limited within that. So that's, of course, an advantage. So the geosynthetic encasement helps to mobilize additional stresses internally inside the column. When it comes to group GCs, right, triangular pattern, it was seen that higher stresses are mobilized inside the case of group arrangement due to the confining effect. So the top picture shows OGC, ordinary granular column, and the bottom one, EGC. That's the only difference there. Everything else remains the same. The box diameter, the granular column diameter, etc. remains the same. The only difference is that top picture is OGC and the bottom picture is EGC, right? So comparing these two pictures, you can see that the confining effect in the triangle pattern is also limited within the granular column, right? Same thing goes with the square pattern as well, right? A group granular column and square pattern, triangular arrangement, I mean, the encasement is found to give you a better result, right? Higher shear strengths are mobilized in case of square arrangement compared to the triangular arrangement. And from this test, it was found that EGC in triangular is better suited for field applications. Whereas two advantages here. One is that encasement is trying to invite every stresses into that. Second is that you have the confining effect of the group granular columns, right? So two advantages. This is just the FLAC output where you can visualize the failure pattern. You can visualize that the failure mode 1 is represented here where it goes completely tear off, and this is the same thing, completely tear off, but in square arrangement, right? 50C is the first picture, which means at the center you have a 50 millimeter column. 50S is the bottom picture where you have the square pattern. So in both these pictures, you can see that it's completely tear off, right? OGCs undergo complete rupture at the failure plane. I'll skip this result here because it goes quite deeper into it, for which we don't have time, I guess, now. Yeah, I'd invite your attention to this picture, just the picture. We'll have these conclusions later because the previous picture had shown the tearing off, whereas in this picture, encasement gives you a bending pattern, right? A bending pattern at 15 kPa and almost a bending pattern at 75 kPa, right? Higher the stresses, it tends to bend out, not to shear off. So the failure mechanism of EGC can be said to depend on the normal pressure. When you vary the pressure, the normal pressure sigma n from 15 to 75, the failure pattern tends to vary, right? At the lower normal pressure, the 15 Pascal, kilopascal, it was like a rigid body, right? You can see that it tends to behave like a rigid body. Whereas with an increase in stress, it kind of, with an increase in normal stress up to 75%, the normal pressure, the tilting of granular column is prevented, right? So that's one conclusion that you can get using the variation of stresses. Again, the application, since these tests were limited to the direct shear boxes, we augmented that to field case as well. Not that they have done the field test, it's just that the literature survey was carried out, and based on the validated literature, a model was developed, which is not based on the direct shear test, but instead like this, right? The literature was published, and I mean the data from the literature published was taken and was used to simulate a numerical model like this, the figure that you see to the bottom right corner, right? You have the embankment of 10 meter, which means it's an axisymmetric. You have 10 here, 10 there, and the depth turns out to be around 17 meters, and the stone columns were installed there. And this was again, FLAC was used to analyze the failure patterns and the modes of failure. OGC is given in the top picture. EGC, encased granular column, is given in the bottom picture. You can get a flavor of the pattern of stresses getting into the soil there. If you take a look at the top picture, you can see that the stresses tend to go into the soil, right, the foundation soil. Whereas if you take a look at the bottom picture, where the stone columns are encapsulated, encased, they tend to limit the stresses within themselves, right, keeping the soil safe. Right, higher shear strains are mobilized below the crest of the embankment, which means below the crest of the embankment, higher shear stresses are mobilized here instead at the toe. Lateral soil movements are restrained by the EGC, which improves the bearing capacity of the foundation soil. Again, it's an advantage. We don't want the soil to get damaged. We want the loads to be taken by the stone column. So there's obviously a reduction in settlement of the embankment, right? Since the embankment foundation soil is not deforming, of course, it gets reflected in the embankment as well. Had the foundation soil deformed or had it been under stress, the embankment would obviously get settled. Now, in this case, since you don't have such a case, the settlement is minimum. Now, the effect of area replacement ratio is also given here. The top picture you see, you have 0.8 meter diameter granular column, whereas in the bottom picture, you have a 1.4 meter diameter column, almost double the size, which means the area of the soil, excuse me, the area of the soil which is involved in the foundation base is almost replaced by the granular column, right? So if you take these two comparisons, you can see that when the diameter is small, the failure pattern is like this, like just like the deep-seated failure. It starts from the embankment top, goes all the way down the foundation soil, and it tries to have a deep-seated failure there. Whereas when you replace with a higher replacement ratio, which means you are using a bigger diameter stone columns, the stresses are limited to this area, right? Which means you're not stressing the foundation soil, which means the foundation soil is strong, and the stresses are limited to the top surface of the slope, right? Again, that's an advantage, but we can't afford to have 1.4 meter diameter for the simple reason that it takes a toll on the economy, right? So you have to have a balance between the 0.8 and 1.4 meter diameter granular column. So this is a observation from this picture. Increase in area replacement ratio, AS, considerably increases the factor of safety, FS, as EGCs effectively prevent the natural flow of the soil, right? Which you can see from the picture. Now, the failure pattern, like I said, you can see from the picture, it changes from a deep-seated failure to a failure that passes to the toe through the embankment. So you don't have the risk of the foundation soil getting failed. If there's any failure, that's limited to the embankment, which we can, at least to a certain extent, repair and replace. Now, the installation pattern, triangular installation pattern is shown to the top with a square pattern at the bottom. Triangular pattern is shown there at the top with an area replacement ratio of 9.42, whereas the bottom picture shows a 12.56 area replacement ratio, right, for a square pattern. And it was found that square arrangement gave a higher factor of safety compared to the triangular arrangement in case of both the OGCs and the EGCs. Of course, again, that's quite intuitive because when you compare the area replacement ratio, you can see that in square, it's a higher area replacement ratio. So obviously, it gets reflected to the factor of safety as well. Now, similar observations were reported from large direct shear and the effect of length of the granular column. Like the previous slide shows that the granular column was around 10 to 12 meters, right? So when you try to reduce the length of the granular column, the factor of safety, which is marked on the y-axis, tends to reduce, right? For the same parameters kept constant, the same diameter, same phi values, same cohesion values kept constant, these the variation in the length from 5 to 11 meters is shown here, and the factor of safety is found to increase with the length of the granular column. So the factor of safety reduces considerably with reduction in length, which means it increases with an increase in the length of the column. Again, that's a reflection based on the previous slide. It's quite intuitive, right? When you have a longer column, uh, that column is kept in such a way that the failure surface passes through that column, right? Whereas when you have a short column, when the length of the column is quite short, the failure surface would probably be passing below that, right? So it doesn't matter even if it's a column up above that or not. To have a longer column, a designed longer column to have a higher factor of safety. I think this is the last slide, I believe. Yeah, this is a mechanism of OGC and EGC, right? To the top picture, you can see a 0.8 meter diameter OGC, and to the bottom picture, you have a bigger OGC of a bigger diameter. You can see that the deep-seated failure tends, to the top picture, you can see that deep-seated failure tends to bend the OGCs towards the toe, and towards the center of the embankment, it's highly under axial stress, right? So the stone columns at the center are acted upon by axial stress, whereas towards the toe, it's predominantly the shear stresses, right? The bending stresses. And when you replace it with the bigger diameter stone column, you have a different pattern here as well. You are trying to restrict the failure to the top level, right? So the GC, granular column, the toe undergoes a higher lateral movement compared to the columns at the center, which is subjected to compressive loading, right? And which is, of course, expected to bulge out, whereas at the toe, you don't expect it to be bulge out. Instead, it tends to bend, just like the long column, right? And second mechanism observation is that the encasement of the GC has increased the stiffness, thus attracting the larger forces. This we have already discussed, right? When you encase a stone column, it attracts the stresses, keeping the soil safe. Now, this is beneficial as the larger percentage of embankment loads transfer to the granular column, thus reducing the overall stresses on the foundation soil. Some conclusions based on the second part is that the stiffer geosynthetic materials helps to reduce the chance of deep-seated failure and keeping the foundation soil safe. Second, when you use a granular column, you can reduce the stresses, transfer the foundation soil, reducing the soil foundation pressures, right? So you're attracting to the stone columns. Plus, I'd also say that when you have a granular column, it aids the consolidation settlement as well. Third observation is geosynthetic encasement helps prevent a rupture of the granular columns along the predetermined failure plane, which you probably might have seen in the comparison between the type 1 and the type 2 failure, right? In type 1 failure, it tries to shear off along the predetermined failure direction, whereas in type 2, when you have an encasement, it offers resistance against the shearing off. So that's another advantage. Yeah. So those who have not up till now, these are the potential takeaways from the talk, and those who are sleeping can wake up, by the way. Yeah, the potential takeaways, I used to have this slide just to summarize everything. You identify a problem, and you understand the mechanism, right? Once you identify the problem, you understand the mechanism, basic mechanism, and you grasp the theory behind that mechanism. You try to play around with different solutions, you think of different perspectives at which this problem can be solved. You come up with one such solution, one such method. You try to conduct research on it with whatever little resources you have, and you arrive at a solution, right? You refine it and arrive at a solution. For instance, when you identify a problem at Cochin Marine Clay, you are understanding the mechanism, right? The mechanism that you understand is that the Cochin Marine Clay will have a cohesion of, let's say, 20-30 kPa, and you grasp the theory, which means you understand that when you can have an option to get the advantage out of that cohesive strength, you think about alpha term, right? So if it's pile to soil interaction, alpha is less than 1, let's say 0.6. Whereas if it's soil to soil interaction, alpha is 1. So that's the way in which you identify the theory behind that. And you learn the different solutions. Under pile is one such solution, double under pile is another solution, and the proposed pile, the new one, is an altogether new solution. You conduct research on it by different iterations that you carry out. You refine it, and finally you contribute to whatever little way you can to the industry or the academy. So that's the first option of the talk. Of course, the second option is this. Right. So I think I'm done with that. Thank you for your patient listening, by the way. And yeah, if there's any queries, I request. Yeah.
Yeah, thank you, Dr. Balu. It was a very nice presentation, and you presented it in a very interesting way. And I don't think that as what you have doubted in your introductory slides, the audience might have gone into sleep mode. Absolutely, that wouldn't have happened, I hope, because we have started getting very good feedbacks, and even queries have started being posted in the midway of your presentation itself. So I think you have done justice to Einstein and also to the audience, explaining things in a very simple way. And now it's time that you
That's a
pay
very
for
good
this.
compliment. I'm not sure.
Yeah, you have to pay for this, Dr. Balu. We have a lot more questions to come. Oh, whatever you
Oh my
have been
God.
doing for the
Okay.
last
I'll wait.
couple of hours, just pay a big price for that. Anyway, I'll hand over to Dr. Bharati Raj. You can coordinate with Dr. Balu for the queries what has been posted in our chat session, teacher.
Yes, sure.
Yeah.
So, one request was,
Yeah, hi,
is there any video available regarding ESC or EGC construction? Then could you please share that?
Oh, I'm afraid I don't have it with me now, but if you have a group, I can share it with them. I mean, now I don't have a video with me in handy.
Okay, sure.
Yeah.
Then coming to the questions, how was the spacing of underreams ensured in field? Is there any example of bulb piles being used in India?
Of course, two questions. Number one is the spacing, right? The spacing stipulated by code was 1.25 times the bulb diameter. Now, how we ensure is that, see, people who are working in the field would probably identify that once you, yeah, let me turn on my camera. Yeah, what you really do in field is that you dig up the hole, right? A shaft is created there. You lower the underream tool into that to the bottommost layer, which means for in our case it's 4.5 meter depth. So you lower the underreaming tool to the 4.5 meter depth, and you cut the clay layer, right? Once you've cut the bottommost bulb, you raise the underreaming tool, so you have some mechanism, some scale mechanism at the top by which you try to pull the underreaming tube upward, right? And that's one option, but that is only applicable when you have a restraining mechanism at the bottom. The practice that we do at field is we construct it from top to bottom, which means the topmost bulb is cut first, right? For example, I have a 4.5 meter long pile. The first bulb, let's assume that's at 2 meter, right? So I dig a hole up to 2 meter, take out the excavated soil, lower the underreaming tool. So that underreaming tool now rests at the borehole bottom, right? Once that rests at the borehole bottom, I kind of I jack the mechanism down such that it gets like this, right? Just like an umbrella, and then cut, right? You take out that soil which that you've cut upward. So that's your first bulb at the top. Now what you do is you excavate the soil downward to 60, in our case, 62.5 centimeter lower. And now the new borehole bottom is 62.5 centimeter lower than the bulb that was already cut. So you lower the underreaming tool again, then you cut the same thing. So that's how you work in the field, from top to bottom. That was the first question. I'm sorry, I skipped the second question. What was the second question?
Is there any example of bulb piles being used in India?
Sure, of course. Bulb piles, even a few Even a few months back, I was involved in an underlying pilot. It was in Kumaragam. I'm sure you've heard about Kumaragam. Kumaragam is also infamous or probably notorious for this clay soil. So uh, even in Kumaragam, it was done a few months back, I believe. It's practical and it's in field, but it's not very popular here because we're all skeptic. Like I said, it's not completely practical in sand. It's completely practical in clay, right? Because you have to ensure that the cavity that you've created due to the underreaming is not collapsed. I hope you agree. We can visualize that, right? You are trying to excavate the soil, and if it's sand, it doesn't gets created, right? If it's clay, it can have a chance of self-standing. So when you can have properly stabilized clay soil with bentonite slurry, you can definitely have that. Of course, it's practiced in India, but I should admit it's not as popular as a usual broadcast institute. Right? It's in practice.
Uh, Next is posted by Ajay Kumar sir. Is it possible to provide uh, underream bulbs in end bearing piles? What will it be? What will be its effect?
I'm sorry, I didn't hear what it was. Is it possible to that in what?
Is it possible to provide underreamed bulbs in end bearing piles?
N bearing piles, yes, of course, but it depends on the N value, right? N bearing pile, again, you design a pile as N bearing if you have, let's say, an N value of greater than, let's say, 15, right? So if it's rock, definitely not possible. But if you have a N bearing pile designed in such a way that the soil is able to be cut out, it can definitely be possible. But again, it depends on the N value, I'd say. N value is nothing but the representation of the density. It just represents the ability by which you can cut the soil. So it depends on the N value. It can definitely be done.
How the diameter of underreams can be found out?
Uh, that is a very vague question. How can that be found out in a sense? Is it, what you mean is it about the designing or is it about the field application?
Maybe how it can be fixed.
How it can be
Maybe.
fixed?
Fixing the diameter is quite simple. See, the example that I've listed out is a 30 centimeter diameter shaft with a 80 centimeter diameter bulb. That's a normal underring, which turns out to be around 2.5 times, right? So even that, there's a code specification. 2 to 2.5 times the shaft diameter is a bulb diameter. But the study I presented was with a lower diameter because that was the key point. Lower the diameter, lower the material input. So in short, in a nutshell, it's 2 to 2.5 times the diameter of the shaft.
Sridevi ma'am has asked, how far is shotcreting a solution for embankment to roads when steep slope is provided as seen in many highways?
Well, shortcreting, it's definitely a possibility, but people tend to go for other methods. For instance, if you have traveled from not sure what volume of audience here are Malayalis, but still, if you have a chance to travel between Thrissur and Palakkad, you can see that there's a road embankment constructed. They tend to design it in such a way that you don't have shortcreting, it's an embankment nonetheless. Even in such cases, you can have shortcreting, but shortcreting is applicable when you have natural embankments, right? Not the constructed embankments. It's definitely possible. I have a few pictures. I'm not sure if it's in my laptop. Shortcreting was done to stabilize a church recently. Not recently, I beg your pardon. It was 2 years back. The site is near Pala. You have it's Marangatupalli. Yeah, Marangatupalli. I was not involved in that, by the way, I should admit. But the church was situated on an embankment, and that embankment was stabilized using shortcreting plus soil nailing. So I do have a photo of that. That's quite near the house of K.R. Narayan, our former president. even I should admit I don't have a photo of that in my laptop now, but I think I have in my mobile, so I can share that as well. I have noted that it can be done, sure.
Uh, Next is it possible to make many reams without disturbing the soil in between?
Practically not, without disturbing the soiling.
In between. In
I
between the
didn't hear what.
reams.
In between the reams, no, it's see, the pictures that I had shown was an AutoCAD drawing, right? You can't expect that to happen in field unless it's quite stiff clay, right? So these representational images are just representational. So that's why we try to do the pile integrity test, right? Pile integrity test would give you an idea whether the bulb is formed or not. So in actual field practices, under ream pile, let's say, yeah, I have an under ream pile with a bulb of 80 centimeter diameter. Once casted, that 80 centimeter might not be of a proper shape because a few clay particles might have fallen off. A few clay particles might have mixed with the bentonite. So these things are possible, right? These things are possible. So it's not always possible for us to construct very beautiful under ream piles, just like the picture that you've seen in the AutoCAD. But nonetheless, under-ream piles are practically possible with more than 2 bulbs. It can be possible. It is possible.
Next is by Raji ma'am. Have you considered the uplift effect of pile while modeling it?
I do have the data with me. The uplift capacity was also designed, I mean, not designed, analyzed in Praxis 2D and 3D. It's available as a conference paper, by the way. The uplift capacity of multi-under-ream pile was a paper name, I guess. It was done. See, again, that's the same story. Even if it's an ultimate uplift capacity, the same cohesion gets mobilized, not the adhesion. Alpha will be the same. Alpha will be 1. It's soil to soil interaction. The only difference is that you don't have the end bearing at the bottom, and plus you'll have to consider the effect of buoyancy and the self weight of the pile while you design the uplift, right? You're trying to get that uplifted. So I do have a paper on that.
Next is why the load test results done in Plaxis 2D and 3D show some difference, and which is more close to the real-time scenario. Should I repeat it?
The difference, no, I get the point. The difference is 2 things. Number 1, again, Plaxis 2D was done in 2012, and during that time, the 2D option had an option for mesh refinement, right? Mesh refinement means that when you click on a line, let's say the pile interface, the mesh around that gets refined, which means you have smaller meshes around. So that refinement option is not available, I'm afraid, in the 3D version. Instead, it accommodates for those effects automatically, number 1. Number 2, Plaxis 2D is a case where you design it as an axisymmetric case, right? For 30 centimeter diameter pile, you just model 15 centimeter, and it's axisymmetric in behavior. Whereas in 3D Plaxis, you are entirely modeling the whole volume. Maybe a few of that errors might have crept in. That could probably be the reason. Now, Plaxis 3D is more dependable compared to 2D.
Is it possible to reduce the length of the pile by providing under reams?
Of course it is, because every pile takes the load in 2 behaviors, end bearing and skin friction. So by providing a bulb at the bottom, you are fundamentally increasing the end bearing, which means the load that has to be taken by the shaft friction can be lowered, which in turn means that you can limit the length, right? So when you have a conventional pile of, let's say, 20 meters, it might take a skin friction of, let's say, around 50 tons, and an end bearing of, again, 50 tons. So when you can limit the length to, let's say 10 meters, and provide a bulb at the bottom, you're fundamentally increasing the end bearing, right? So that increase in end bearing can be compromised on the shaft friction or the length. But all these things depends on the field conditions. That's a cautionary note that I'd like to add. It depends on the field conditions. No field condition is pure clay. No field condition is pure sand. Everything is a mix of both.
Okay, next is how did you define interaction between soil and pile between the reams in numerical analysis?
Yeah, there's a factor called R inter. If you are familiar with the software, you can see an option called R inter. Reduction factor at the interface is what they call. It's nothing but tan delta. So when you have a soil of phi, angle of internal friction, 30 degrees, you can expect delta to be around, let's say, 17 or at most 20. So tan delta is nothing but R inter, which means if you want to accommodate that tan delta, you provide an R inter of 0.6 or 0.7, whatever value that you get corresponding to 10, 20 degrees. So that's an option in the software. I guess that addresses the problem.
Okay. Shekhar sir has asked, can underreams be used for soft clays or whether it can be confined only to stiff clays?
I would not suggest this for soft clays because the problem in the field is to make sure the cavity remains stable, right? Even in stiff clays, you provide bentonite slurry, right? Bentonite slurry is the one that stabilizes the cavity. So in soft clay, again, softness is a relative term. It depends on the consistency and the cohesion, but nonetheless, in a broad perspective, I'd say we don't recommend it for soft clays for this simple reason that the cavity can't stand on its own.
A couple of questions more. Is it possible to construct underreamed piles in waterlogged areas?
Yes, definitely. Of course,
and
there's examples that, yeah.
How do you ensure the shape of the bulb if the water content is very high?
Yeah, two parts of the question. Number one, it can be constructed in waterlogged areas because the examples that I listed, Chennai and Kochi, they're all waterlogged. Usually in Cochin or Komaragam side, you can expect the groundwater table to be around, let's say, 2 meters. The test that I've listed in the research had the water level at 2 meters, I believe, and the pile length was 4.5 meters, right? So once you go to 2 meters, you encounter water, and below that, you go with the pile. So dewatering is a method, but once you have the bentonite slurry into the soil to stabilize, and you use the trendy pipe to concrete, these will be solved. Water table won't be an issue, at least during the construction. Second question, I'm sorry, I missed that.
How will
do
you
you ensure
the shape of the bulb?
The shape of the bulb, like I said, we should admit that you can't expect the shape to be as good as you have seen in the model, right? And the one way of ensuring is that you lower the underreaming tool and you cut the underreaming bulb, and the soil that was cut falls into the bucket. You have a bucket there, right? The underreaming tool has a bucket below. One method to ensure that is a volume of the volume of soil that you have collected into the bucket. If it's in line with the volume of the bulb, you can expect. That is one rough method. Now, we actually thought pile integrity test, PIT, was one method, but it didn't work. Pile integrity test we thought would give you the diameter, but it didn't give the diameter. It gave just the length of the pile. So I believe the first method could be an option. I'm not quite sure if PIT, the pile integrity test method now, has got some advancements by which you can estimate the underreaming bulb's diameter, but earlier it didn't have such an option. Profound SIT plus was the PIT method we used, the low strain dynamic test we used. We didn't have such an option there. So I guess the first method of trying to get the volume of soil would probably give you an idea of whether the bulb was properly cut or not.
Next is, can we use geotextiles in Embankment of roads.
Embankment of roads, of course. I think, yeah, see, like I said, if you travel from Alapi to Chengnasheri, you can see a few stretches where there's a association with the Koya board, and they have used the Koya geotextiles. They have laid the Koya geotextiles. That's a natural geotextile, by the way, to have the slope stable. And artificial geotextiles are also used. Yeah, a few days back, I had attended one such FDP. It's not an FDP, it was a workshop by Professor Rajagopal of IIT Madras. I was a part of that. And the case study that he did present for us was the Kannur airport, right? They had a very high embankment, and they have used geosynthetic to stabilize that, if I'm not wrong. So it's possible, and it's in practice.
And the last question, is it possible to increase the load carrying capacity by increasing the number of bulbs and reducing the diameter?
Number of bulbs and reducing the diameter. Yeah, that's what we have done, right? So what we've done was, instead of 80 centimeter diameter bulb, we reduced that to 50 centimeter diameter bulb and increase the number of bulb. I mean, I'm so sad to see that there's a question like that, because that was the entire topic all about. You reduce the diameter and then you increase the number of bulbs. I don't know. Yeah, that's what we have done. It's an option, definitely. But see, in the piles that we have in field is not shorter in diameter than 30 centimeter. It's a usual practice to have the diameter from 30 centimeters, 50, 60, etc. Because the auger boring method in practice has some standard dimensions. So 30 centimeter is the starting dimension of the shaft. So you don't usually go below that unless it's a borehole, right? The borehole, you have 20 centimeter diameter. So the borehole is just for us to carry out the SPT test, not for pile casting. So 30 centimeter is a good option.
So I think that's all.
Is that all? Thank you so much.
Yeah.
Uh,
Yeah, I think we have come to the end of the session. All the queries posted are answered by our resource person. I think if the audience has any more questions, he is ready to face, it seems. So otherwise, we'll wind up the session. Yeah. Yeah. Okay. So yeah.
Disha ma'am,
Yeah, please. Yeah. Yeah, thank you. Thank you, Dr. Balu George. First of all, I would like to express sincere thanks on behalf of Department of Civil Engineering, NSS College of Engineering, Palakkad. And I'm very happy to say that you have done a very excellent presentation. The content was sufficient enough and it was beautifully presented. And I think we have more takeaways, both with respect to the content and also in the style of presentation. So thank you for accepting our invitation and being a part of this faculty development program, delivering a wonderful talk to our participants.
Thank you so much.
Yeah.
Thank you. In fact, I should thank you all for inviting me and having me here, because honestly, I don't think I'm worthy enough of being alongside with the strong bench of speakers that you have robbed in for the presentation. I don't think I was worthy enough, but it was gracious enough from your side to invite me and give me a chance to share whatever little I have shared now for 2.5 hours. Perhaps I believe I've not gone over 4 p.m.
No. You are on right time.
Dr.
Thank you
Balu,
so much. Thank you for the
it
patience as well.
was it was really
Yeah.
one of the most interesting sessions, and also thank you so much for that excellent presentation and the
Good
interesting
to hear
topic
that. Thank
that you
you.
had taken. Because throughout the sessions we were hearing, we were dealing only with concrete, and it was it was quite different to hear from a geotechnical point of view.
Stream.
Yeah.
Yeah, Kirti teacher, if you have something to add to the resource person.
Yeah. Thank you, Dr. Balu.
Thank you, ma'am.
So thank you. Yes, Bharati Miss said, we were all the while dealing with concrete. All the participants were thinking on, okay, concrete is only the thing. But then we could nicely hear something from the
I wouldn't be able to cast a
geotechnical
kite without a
side.
concrete, so I can blame concrete. Pile is concrete.
Yeah, that's true. That's
That's
true.
true.
But
That's
still,
quite true. But still,
the word
that's
concrete is been less used. So So thank you once again from all the coordinators side as well as from the department side. Thank you.
Okay.
Thank you for
Thank
joining
you. Thank you
us.
for having me. Have a great day. Thank you.
Yeah, thank you.
Thank
Thank
you
you,
so
Dr.
much.
Balu. Yeah, then you may please leave the call, Balu.
Thank you.
So participants, the feedback form has been posted in the chat box. So here we come to the end of the 8th session, and tomorrow the session will start at
10
10,
o'clock.
and the link will be posted by 9:45. Please join us.
And
Thank you.
and also we have the second session. Second session will be will not at 2 o'clock. It will be it will be at 1:30. It will start at 1:30. So kindly note that.
Yeah, true, true.
So please join us for both the sessions. Thank you.
So thank you all.
Yeah.